assume that the system is gapped. That is, there is a non-zero separation between the ground state and the continuum of excited states. But this ground states may be degenerate, as we will see. And then I apply this insertion of adiabatic insertion of.
Excuse me, Masaki.
Yeah.
Masaki, do you intend just to show us a picture of Stockholm, or are you going to show us the next slide?
No, this is my only picture of Stockholm.
No, will you be moving to the next slide? We're worried that it's stuck.
Sorry. I didn't get it. On my screen, it's moving.
No, we are only seeing Stockholm, which is a very nice picture, but that's the only.
Oh, okay. Sorry. I didn't realize. Okay. Apparently, there is some problem. So maybe I will leave the session, then rejoin. So.
Okay. Very good.
Yeah. Sorry,
A small station break.
So, do you see the?
We see the first slide. We just see Stockholm at the moment.
Okay. Again, so I changed the page. So you are still seeing the Stockholm?
Yes.
Strange. What's going on? So still the same?
No, now we see Flux insertion.
Oh, okay. Somehow when I make this full screen on my site.
Yes.
So are you seeing the adiabatic flux insertion now?
Yes, we are.
And now I have square lattice. Do you see the square lattice?
Unfortunately not.
No, okay. So maybe full screen. What's going on? Well,
maybe just do it like this. This will be all right.
Okay. Then
okay. Yeah.
Okay. So you can see the page. Adiabatic flux insertion.
I haven't seen the page before that though yet. Yes. Okay. If you start there.
Okay.
Yes.
Okay. Sorry about that. Yeah, I didn't get it because apparently there was no problem on my side. Okay. So, well, but this was just recap of last week. So I do adiabatic flux insertion. Then generally the ground state evolves to some other state. But we are in the different gauge. So in order to go back to the original Hamiltonian, you need to apply this large gauge transformation. Then I want to apply this argument to the many particle on periodic lattice, like a square lattice. And let's say the size of this system is Lx times Ly. And then I insert this flux adiabatically, unit flux quantum. So when the system has periodicity, that means that in other words, we have lattice translation symmetry in this system. So when we have symmetry in the system, then we have some conserved quantity. And so if we have translation invariance, then momentum conservation follows. And maybe it's easier to think about this in continuous space. If you have continuous translation invariance, then momentum is conserved, and the momentum is given by minus I times derivative. But in the lattice, we have only discrete translation symmetry. So if Tx is a operator translating by one unit cell or lattice constant, the momentum P can be defined in this way. Exponential of IP is equal to the translation symmetry. So then now I do the adiabatic flux insertion, but I can choose a gauge which is uniform, that is order AX, which is defined on each link, is given by this proportional to the time. So when T reaches capital T, then you insert unit flux quantum. But in this gauge, the Hamiltonian is always translation invariant. So momentum is exactly conserved. So if the initial state has momentum px0, then even after the adiabatic flux insertion, the momentum is still exactly the same number. So which is a bit confusing, but we have to be careful that the momentum can mean different things. So in the previous slide, what I introduced is basically canonical momentum, so to speak. But often we consider kinetic momentum, that is minus I times derivative minus vector potential. And this corresponds to the parallel transport if you attended last week. So this is covariant derivative. So this is gauge invariant. On the other hand, this canonical momentum is not gauge invariant. So if you apply large gauge transformation, the canonical momentum changes. But often it's convenient also to use canonical momentum because in order to use the translation invariance, this canonical momentum is more useful. So what we do is I start from initial ground state and insert unit flux quantum adiabatically. Then I assume that the gap doesn't close during the flux insertion. So ground state must end up with ground state. But this final state is generally can be different from the ground state. But as I just mentioned, the momentum is exactly conserved. So the final state after the flux insertion must have the same momentum eigenvalue px0. But as I noticed several times, so after flux insertion, we are in the different gauge. Hamiltonian is H with 2 pi flux, which is different from this Hamiltonian. So you cannot directly compare these two momentum because you are in the different gauge. So you now do the large gauge transformation to this final state. Then you obtain another state. So this must be a ground state of original Hamiltonian. But now because of this large gauge transformation, the momentum eigenvalue of this state is different, can be different from the original. And that can be easily computed using this commutation relation between large gauge transformation and the translation operator, because large gauge transformation is given by this, the x coordinate times particle number operator. So if you have U inverse U, they cancel. But if you put the translation operator in the middle, then you shift all the coordinates by 1. So this x is shifted to x plus 1, then which does not cancel exactly with this. So you have some extra factor, which is exponential of 2 pi I over Lx times summation of NR. But this is sum of particle number, so which is total number of particles, which is conserved quantity. So if you use this, then momentum of the final state after the large gauge transformation is shifted from the original value by this quantity. So we get this momentum shift, and this is a total number of particles which is conserved. Then we are usually interested not in specific system size like 32 by 33, but we are usually interested in a thermodynamic limit for a fixed particle density, that is particle number per unit cell. In this case of square lat is particle number per site. So let's nu to be a particle number per site. Then suppose this particle number per site density is P over Q. P and Q are integers, coprimes. then this momentum shift is 2 pi over Lx times a number of sites, Lx times Ly times density. So Lx cancels, but Ly survives. So the momentum shift is 2 pi times Ly times P over Q. So that means that if you choose this Ly system size to be coprime, so no common factor with Q, then this is still non-trivial fraction number, not integer. And the momentum is defined modulo integer, but this is fractional number. So that means that after doing adiabatic insertion of unit flux quantum and large gauge transformation, then final state must have different momentum from the initial state. So if the final state is also ground state, then this ground state must be different from the original initial ground state. So that means that you must have ground state degeneracy. So from this argument, so we have some very general constraint on spectrum of many-body Hamiltonian on periodic lattice. That is, so I just assume periodicity or translation invariance and particle number conservation. Then you can define the filling fraction, that is number of particle per unit cell. And if this is fractional, then there are two possibilities. Either the system is gapless, or if the system is gapped, then the system must have a Q-fold degenerate ground state. So what is excluded is that you cannot have a unique ground state with gap if the particle number density is fractional. So this is, in some sense, shows ingappability of the system. And this kind of theorem is called Lipschutz-Matisse theorem, or generalization of it. So, okay, so probably many people are familiar with this, so I shouldn't spend too much time on this, but this has a long history. So originally it was just a small theorem for spin one half chain, but gradually extended the range of applications. And now there is more rigorous proof. So you don't really need flux insertion argument because there are now more rigorous proof. But I think it's still kind of intuitive, so it's useful in extending more, finding more applications. Yeah, there is a question. Yeah, for finite L, the levels are discrete, and there is always a gap formula. Yeah, so okay, so it's tricky stuff. So yeah, this argument is never really mathematically rigorous, but what I mean is that by gapless, I mean, of course, if you fix the system size L, then generically there is always some gap. But this gap can be order of, let's say, order of 1 over L or 1 over L square or something. So which can go to 0 as you go to larger system size, samodite limit. So what I'm saying as gap in this context is there is some lower bound of the excitation gap. And for any large system size L, the gap is bigger than this lower bound, then we can call this lower bound as gap. That's how I distinguish. Okay. So probably many of you are already familiar with this, but as I also mentioned last week, so this kind of argument depends on the crucial assumption that this gap does not close by insertion of the flux. So my argument is something like this. So first I assume the existence of gap. That's fine because otherwise I have gapless excitation. So that's part of the theorem. So it's okay to assume this gap. Then I insert a flux adiabatically. Then after insertion of unit flux quantum, the spectrum must be the same as zero flux. That's exact by gauge invariance. But in principle, you know, somewhere in the middle, the gap may close, or some states might come off from excited states continuum, and maybe you can have a crossing between the excited state and the ground state. Then you switch between ground state and excited state. So if that happens, then you start from this initial state, which is a ground state, and you do the adiabatic flux insertion. And then in principle, you might end up with somewhere in the excitation continuum. If this happens, then I cannot claim the theorems like what I claimed.
There's a question here from Kim. She asks, how does it work in the non-symorphic case? Could you give a brief comment?
Okay, yeah, sorry. So in case of non-symorphic case, so if you define the unit cell, so unit cell is usually defined with respect to the translation invariance only. So the unit cell might be big, but non-symmetric symmetry means that if you do half translation, then deflection, then the lattice is invariant. And actually, I kind of forget, but you can utilize this non-symmetric symmetry by, how did it work? Okay, sorry, I forgot, but there's some clever way of using this non-symmetric symmetry, half translation, deflection, and you can use this symmetry instead of the standard translation symmetry that is. Okay, so sorry, I will try to recall that.
Probably it's like you're allowed to do a lattice operation and a translation at the same time as your modified translation.
Yeah, something like that. Yeah. Okay, there is another question. During adiabatic flux insertion, when the ground state goes to an excited state, then one of the excited states must come down to the ground state. Yeah, right, exactly, yes. So yeah, if this kind of evolution happens, that means that some other state must come down from the excitation continuum and become the ground state, and there is a crossing somewhere because the number of states must be conserved. Yes, but you know, in principle, that can happen. So from now on, I want to show you that this kind of stuff can happen, but it has some consequence. That's what I want to show. So then that's related to the distinction between insulator and conductor. And so the conduction property of the electric conduction property of the system can be characterized by, of course, by conductivity. So the current as a function of frequency and wave number is proportional to the applied electric field. And there is some coefficient which represents the linear response of the system to the applied electric field. So this conductivity is, of course, important quantity you can measure in the experiment and so on. And in particular, here I'm interested in the Q equals 0 component of the conductivity. And so this is a function of frequency omega. Then if you look at textbook or something, then you can find the expression like this. So this sigma omega can be decomposed to 1 over omega pole plus some regular function of omega. So this singularity has some coefficient, generally speaking. And this coefficient is called Drude weight. So of course, you may not have this pole. That means that in that case, this Drude weight is just 0. And actually, this Drude weight is important quantity with which you can distinguish insulator and conductor. And that was already discussed in famous paper by Walter Kohn in 1960s. So basically, this part represents some free conduction of current by electric field. So if D is non-zero, then this means a conductor, or it actually represents some kind of perfect or ideal conductor. So in real system, there are some relaxations, so this delta would become finite. In that case, you have broadened peak. But if you study conductivity as a function of omega in ideal lattice model with perfect translation symmetry, then often you can find delta equals to infinitesimal. So in that case, if you take a real part of sigma, then you find a delta function peak. And yeah, this delta function peak in real part of the conductivity shows that the system is really ideal perfect conductor. So this is what you can usually find in textbook. But well, this may be also, I don't know, common sense, but for me, this real-time formulation of conductivity and Drude weights is more intuitive. So instead of going to, well, you can always do Fourier transform and go to frequency space, but you can also write the conductivity as a function of time. That is current density you measure at time t. So within linear response theory is you know, the response to the linear response to the applied electric field. But this response can happen with some time delay. So current density at time t can be affected by electric field at time t prime, as long as t prime is less than t because of the causality. So you have this convolution kernel, and this sigma of t represents current response to the electric field with a given time delay. And of course, if you Fourier transform this sigma of t, then you get the usual sigma as a function of omega. But you can understand the Drude weight in terms of this real-time formulation. That is, so if you consider a system with relaxation and so on, if you consider sigma t as a function of time and send t to infinity, that represents the current response to the electric field, which was applied long time ago. But if your system has some relaxation, then after a long time, the system forgets about applied electric field. So usually sigma t goes to 0 as you send t to infinity. But in perfect conductor, once you apply electric field, you create some current, and this current is perpetual. It's flowing indefinitely. So sometimes sigma t limit for t goes to infinity is non-zero, and this is nothing but Drude weight. So we can consider this kind of setup in the context of flux insertion. So I start from the initial state, let's say at the ground state, and then at t equals 0, I switch on the constant electric field, which can be represented by this vector potential, which is proportional to the time, because electric field is just a time derivative of this vector potential. And this, yeah, so this is a electric field. And this calligraphic AX is a vector potential you obtain after the insertion at the final stage. When time t is equal to capital T, then vector potential becomes this calligraphic way. And in this case, so the current responds to this constant electric field. But if the Drude weight is non-zero, then response to this Drude, well, this ideal response to the electric field just accumulates. So as a result, the current is induced proportionally to T in the presence of this Drude weight and this electric field. If you do this very, very slow. So this is current induced in this setup in this adiabatic ring. Okay. Then now I can relate this induced current with the increase of the energy. There may be some question. Question is, can you generalize this flux insertion to whole? Yeah. That's another thing. Well, actually, Laughlin did this. I forgot to mention maybe, but this whole flux insertion gauge invariance business was initiated by Laughlin. He explained the quantization of whole conductivity in this way. I didn't have time to mention. And recently, I had some modification or maybe improvement of original Laughlin gauge for whole conductivity, although I'm not planning to cover it today. Maybe if you are interested, you can ask me privately. Okay, so the point is that, so we have a current operator, current density operator, but as you know, the current density operator you can obtain by differentiating Hamiltonian by vector potential. Then you get a current operator. So the current density, you differentiate Hamiltonian by vector potential, then divide by volume of the system. But if you are inserting a flux at a constant rate, then vector potential is proportional to the time. So in this setting, the current operator can be related to the time derivative of the Hamiltonian. So you get some factor because AX and T are related. So for adiabatic flux insertion, now I want to evaluate how much energy the system gains by doing this adiabatic flux insertion. So you just integrate derivative of Hamiltonian by time, because the Hamiltonian is energy, and integrate this dH dt from t equals 0 to t equal to capital T. Then you get the energy difference between the final state and the initial state. And this energy difference is not affected by large gauge transformation. But because of this relation, this dH dt can be written in terms of current times this dA dt, but dA dt is given by this final state vector potential over this length of the process, time length of the process t, so AX over t. And then I have Jx, so I just integrate Jx from 0 to t. But now I assume that the system may have Drude weight. Okay, the system may have a 0 Drude weight, but anyway, if you consider adiabatic process, then all other component of the conductivity kind of dies off, and only this Drude component survives after a long time if you insert a flux very slowly. So in this case, the current can be written by Drude weight times this T linear function. So you just plug in, and then you can do integration. So of course you get T square over 2, and then this T square cancels with this. So at the end of the day, you have a relation between the energy increase to the Drude weight. So the energy increase during the adiabatic flux insertion, delta E is proportional to actually Drude weight, and the proportionality constant is given by volume over Lx, the system size in x direction squared, times this flux squared. We must assume T del. Okay, right. Yeah. So here I assume delta Drude broadening is really 0, which is of course not the case in the realistic system, but if we want to study some lattice model, well-defined lattice model, then delta can be considered as infinitesimal. If GS, yeah, so that's a point. So yeah, okay. So last question, I'm going to say something related in the next slide. So then I will come back to your question, but if I was forgetting it, please remind me. Okay, so actually the problem is depends on the dimensionality, but yeah, this was my motivation. So I assume that system has a gap. So after insertion of 2 pi flux, the spectrum must be identical to the 0 flux. But as I mentioned, the in principle, by adiabatic evolution, the ground state might end up with somewhere in the excited states, in which case you must have a gap closing or level crossing between excited states and the ground state. But yeah, last question is related to this. So if I assume that the gap does not close by flux, then this cannot happen. But that assumption is non-trivial. So, and actually, I think sometimes this gap closing happens. But my point is that if this kind of scenario is realized, then the system gains some finite energy by non-zero energy by this adiabatic flux insertion. Then it has a non-trivial consequence on the conduction property, especially in 2 dimensions. So, sorry, I went back. Yeah, so, okay, sorry. I wanted to show this. Yeah. So, yeah, especially in 2 dimensions, this is interesting because this energy gain during the adiabatic evolution is related to Drude weight. But this phi 0 is just a constant 2 pi, so it's not so important. But this factor is volume divided by system size in x direction squared. So if you take a isotropic system, the size in x, y, z direction roughly the same, then this is of order of length to d minus 2. So actually for 2 dimension, volume and Lx square are of the same order. So this is order 1 quantity, which means that the Drude weight is basically constant times energy gain. So in 2 dimension, if you have a gap, and if you have gap closing and your ground state evolves into some excited states by adiabatic evolution, then we can say that, okay, this system must have non-zero positive Drude weight, which means that the system must be conductor in this sense. So in other words, if you assume your system is insulator, then this cannot happen. So the ground state must remain in the ground state. So in that case, the non-trivial assumption I made for Lipschutz-Matisse theorem or fractionalization and so on is really satisfied. So I can replace that assumption of non-gap closing by flux by the physical assumption that the system is insulator in the sense that Drude weight is 0. So this is one way I can justify this assumption I have made previously. Yeah. So follow up on Yasha's question. There is a question on chat. yeah, I'm still confused on the meaning of the word adiabatic for gapless systems. Well, okay, so yeah, here I'm doing this for gap system. Yeah, for gapless system, it's tricky. Maybe we can still define in some way, but so here I'm assuming that T is you know, bigger than inverse of the gap. So once you assume the existence of gap, I think we can. Well, okay. So well, if this happens somewhere, the gap must close. Well, okay. So yeah, I don't know how rigorous I can make my statements, but well, in this discussion, yeah, so yeah, T I supposed to take larger than any time scale, I guess. Yeah, even bigger than finite size gap, inverse of finite size gap in this case. Yes. Okay, yeah, maybe I'm not, yeah, answering your concern properly, but yeah, maybe we can discuss later. Okay. So okay, so from this, especially in 2D, the physical assumption of a system being insulator actually restricts the possible adiabatic evolution of the system. And this is the formula I derived using the insertion of unit flux quantum with periodic boundary condition or torus. But if you go to very large system size, then the vector potential is unit flux quantum divided by the length of the system in x direction. So this goes to 0. So maybe you can Taylor expand this energy as a function of flux or vector potential. So if you do Taylor expansion, then the Drude weight is given by the second derivative of energy by vector potential. Actually, this formula has been known for a very long time. So this is the famous Kohn's formula for Drude weight proposed at least in this paper. So this is very famous paper. But so this is kind of extension of Kohn's formula. But actually, this up to this point, I realized in my paper in 2003, already pretty old paper. But yeah, recently we realized that this can be more generalized. So that is we can extend this idea to nonlinear electric conduction. So for a long time, theorists have been mostly focused on have been focusing on linear response theory, I guess, because linear response is already non-trivial, not easy to calculate conductivity, and it works well, rather surprisingly, to explain many experiments, even when assumption of linear response is not so obvious in experiment, but in many experiments, linear response theory works very well. But recently, experimentalists developed laser apparatus and so on. And if you shine the material by strong laser, then you can observe nonlinear effects and so on. So there are some experimental interests recently on nonlinear effects. And also on theoretical side, there are also several developments. So nonlinear electric conduction is one of the topics of current interest. For example, okay, so this is not directly related to our work, but recently, for example, so-called shift current is discussed. So shift current means that you just shine the strong laser or light to the system, which is AC electric field. But this AC electric field can shift, roughly speaking, positive charge and negative charge in opposite direction. Then this means that you can induce DC current by AC electric field, which is called shift current. And this has application, very practical potential application to photovoltaics and so on. So this is an interesting effect. Okay, so I'm not going to show some result directly relevant to this shift current, but sort of related. That is, if you generalize linear response theory, and then you can include nonlinear response, that is current at time t is not only given by linear response, but the sum of nth order responses. So at nth order, the response is proportional to electric field, n of them, but in general at different times. So with some time delay. And this real-time conductivity, nonlinear conductivity is a function of n times, n delay times. And if you convolute this and the sum over n, then you should be, in principle, you should be able to obtain the current induced by electric field, including the higher order nonlinear conductivities. And once you have this nonlinear conductivity, then you can also define the nonlinear generalization of Drude weights. So that is, so yeah, my notation is not always clear, but I hope it's understandable. So here, the conductivity is a function of real time, delay times. And when you send delay times to infinity, then in relaxation system, the response would die, so it would go to 0. But if you have a perfect conductor or something, then once you induce a current, then some of the current survives for infinite long time. And this limit represents the portion of nonlinear current induced by electric field, which survives for infinitely long time. So this is a nonlinear generalization of Drude weight. Then I can repeat basically the same analysis. That is, I do the adiabatic flux insertion according to the same linear schedule. But now, now I can include the nonlinear part of the current, which is proportional to the nth power of the electric field. And after a long time, only this Drude part survives. So nth order nonlinear Drude weight times this power of nth power of electric field, and then times t to the power n, because effect accumulates as you continue inserting the flux. So this is again a generalization of previous linear conductivity analysis to nonlinear ones. Then I can relate the n+1 order of energy gain during this adiabatic energy insertion to the nth order current contribution to the increase of energy. So again, dH dt can be related to the current, but current is sum over all order contribution. So I'm just picking up nth order response current to the electric field. Then because this nth order current has this particular time dependence, you can integrate over time t, then you get the capital T, which is a length of the adiabatic insertion process to n+1's power divided by n+1. But this t, power of t just cancel with this denominator, which appears as strength of the electric field. So at the end of the day, the higher order term
time t,
yeah,
you get the
sorry, the question was is that the last question? Is it obvious that the nonlinear Drude weight is independent of the order? Well, it's not obvious, I guess, but physically, I think it's natural. So this represents, so if you apply electric field, this electric field induces some current. And as you wait for very long time, some of the current will just go away, but some portion of the current will survive. And this is measuring how much current is surviving. And well, so okay, so in this definition of nonlinear conductivity, all the time arguments enters in equal footing, I guess. So well, still okay. I'm not making mathematically rigorous discussion. So I guess in very rigorous sense, still I'm missing some maybe possibility that this limit depends on the order of limits, but physically I don't expect such dependence. Okay, sorry, and then I was missing another question. So question from Pavel, can you give an example of gap system where gap closes and reopens under Adiabatic? Yeah, good question. So sorry, I was thinking of mentioning this, but then forgotten. So, as I said, in principle, the gap can close and then ground state may end up with excited state. And I think there is, okay, it's two them. Well, yeah, the example I thought about, okay, so, well, first, I don't know any really established example, like some model which shows a gap closing at the intermediate value of phi numerically or something, but what I thought as a possible example, or maybe is that, okay, now I'm not so sure if I can realize this in 2D, but anyway, so suppose you have superconductor, and if you have attractive Hubbard or something, then, the system shows spontaneous symmetry breaking in superconductivity phase, superfluid phase. So you must have a gapless Nunn-Goldstone mode. So you have a gapless system, and that's it. But suppose your system is superconductor coupled to the physical electromagnetic field. Then, as we know, because of the Higgs mechanism or Anderson-Higgs mechanism, the superconductor doesn't have a gap. Sorry, superconductor has a gap. So the Nunn-Goldstone mode would present if we don't consider coupling to gauge field. But once we couple to gauge field, then somehow this dynamical gauge field absorbs the gapless Nunn-Goldstone mode, that we have a gap. And I think in this case, we have a gap, but we have a non-zero superfluid density. Then the Drude weight must be bigger than superfluid density. So we have non-zero Drude weight and gap. In that case, I think this gap closing should occur from this discussion. But I haven't verified with concrete model. I don't know any numerical verification of such thing, but that's the example of gap closing I can think of. Okay, Yasha made a comment. Affleck Marston pi Flux state might be an example. Isn't it gapless, or maybe I misunderstand what you are saying? Yeah, maybe we can discuss later. So, okay, where are we? Okay, so anyway, so what we did here is that we considered the same flux insertion process and then measured how much energy you gain. And energy gain is related to dH dt, time derivative of Hamiltonian, but that can be related to the current. So if you consider higher order response of the current to the electric field, you obtain the higher order correction to the energy gain during the adiabatic flux insertion. So then if you equate the energy dependence, flux or vector potential dependence of the energy eigenvalue, then you can relate the higher order nonlinear Drude weight to the higher order derivative of the energy as a function of flux or vector potential. So if you set n equals 1, this is a very well-known Kohn formula for Drude weight. But similar very compact formula can be obtained for the nonlinear generalization of the Drude weight. Okay. So yeah, I'm close to running out of time, but there are some questions, and yeah, at the start I had some problems, so I hope I can continue for 10 minutes or so.
That's fine. Continue for a while. We've got plenty of time today. Yeah.
Yeah. Okay. So far I have discussed the adiabatic flux insertion, but actually you can do flux insertion at different speeds, like a finite time or so on. But it's also useful to consider the opposite limit. That is, this is opposite limit to adiabatic flux insertion. So in adiabatic flux insertion, you insert a flux very, very slowly, taking very, very long time. But here I consider similar process. So vector potential is proportional to time t over period of time capital T. But I can now send this period of length of the adiabatic, flux insertion process to 0. Then that means that I suddenly insert a flux instantly, bang. This physically corresponds to applying the delta function electric field pulse to the system. And what becomes easy in this limit is that this is a typical case of the so-called sudden switching or quantum quench. So you had 0 flux Hamiltonian, 0 vector potential Hamiltonian, and you had the ground state. But at t equals 0, you suddenly switch on the vector potential. So at t bigger than 0, you have different Hamiltonian, including the vector potential. So this is a variation of quantum quench. And in this case, just after applying the flux, the wave function does not change because basically the wave function cannot catch up with the sudden change in the Hamiltonian. So this is something called sudden approximation in the standard quantum mechanics textbook. But the point is that again, we can say that okay, I switch on the flux suddenly, but the wave function cannot catch up, so the wave function remains the same as before, but we are in a different gauge. So in order to make a meaningful comparison, you should apply the large gauge transformation. So the initial state was ground state, and by sudden switching on flux, the wave function remains in the same state, but in the different gauge. So you apply the large gauge transformation to original ground state. Then this is the post-quench state after inserting the flux instantly, then doing the gauge transformation. And interestingly, you can play the same game. That is, okay, so it happens instantly, but the system still gains some energy. And you can try to evaluate. So on one hand, again, the energy increase is nothing but the dH/dt integrated. And the dH/dt can be related to the current by the same logic, because current is derivative of Hamiltonian by vector potential, and the vector potential is proportional to time. So now you want to integrate this Jx over time, and the Jx, including the nonlinear responses, can be written generally in this way. The real-time conductivity, nonlinear conductivity times nth power of the electric field, because we have constant electric field throughout the process, and do the integral. But now we consider the limit of sudden insertion. This capital T goes to 0. Then, of course, oops. Yeah, this is right. So the arguments of this real-time conductivity, which represents the delay of the response, is also between 0 and capital T, because we are considering very short period of time. So if this function is some continuous function of time, then in this sudden insertion limit, basically we only pick up value of this conductivity at 0 delay time. Because I insert a flux suddenly, that means that I apply the delta function like electric field pulse. But I want to know the value of current only during very short period of time. So I don't need any information about delayed response. I only need information about the instantaneous response, which is nothing but this nth order conductivity at 0 time delay. And I have nth power of electric field. And again, the effect accumulates. So I have time t to nth power. But then I can plug in this formula here, then do the integral easily. And on the other side of the equation, I need an energy increase caused by the sudden insertion of the flux. But actually, this has a nice expression, because as I said, after the insertion of flux, sudden insertion of the flux, and then large gauge transformation, the state wave function becomes ux times the original ground state. So after the insertion, the energy expectation value can be written like this: psi 0 u daga times Hamiltonian times u psi 0. And this can be also interpreted as ground state expectation value of the gauge transformed Hamiltonian, u daga hu. So this is nothing but the expectation of Hamiltonian in the presence of flux by the original ground state. So we just pick up the difference from the original ground state, which is Hamiltonian in the presence of this flux minus original Hamiltonian. Then you take the expectation value with respect to the ground state. So if you are familiar with the original paper by Lipschutz and Matisse, actually this is nothing but Lipschutz-Matisse variational energy. But here, we can interpret this energy as energy increase caused by the sudden insertion of the flux. So again, you can equate these two sides and match order by order. Then you found the relation between this instantaneous response, so the 0 time delay nonlinear conductivity, to the n+1 order derivative of Hamiltonian with respect to the vector potential, then set vector potential to 0. Then you take the expectation value of this guy by the original ground state. So this is different from the Kohn formula, because in Kohn formula, you take the derivative of the energy eigenvalue. But here you take derivative of Hamiltonian as an operator, then take the expectation value by the ground state. So they look similar but different. And by the way, this instantaneous response can be written in frequency space as a frequency integral. Because basically instantaneous response in real time corresponds to frequency integral over minus infinity to plus infinity. So this actually is nothing but so-called F-sum rule of conductivity. And again, the linear, this F-sum rule for linear conductivity is well known, has been discussed over many years. And you can reproduce the well-known F-sum rule for linear conductivity by putting n equals 1. But here, I automatically obtained the F-sum rule for at every order of nonlinear conductivity, like second order, third order, fourth order, whatever. Yeah. And actually, there are some discussion by Shimizu around 2010, 2011. But we think this is more general. And also, in this way, it has very similar looking form to the Kohn formula, nonlinear generalization of Kohn formula, but they are different quantities, and their physical meanings are different. So, so these are very general results, but we did try to test this formula in tight binding model. Okay, so this is tight binding model, so simple system, but still calculation of nonlinear conductivity is not totally trivial. So this is a nonlinear conductivity in XX direction as a function of two frequencies, omega 1, omega 2. So you have some peaks, and this is a linear conductivity as a function of frequency, and this peak in the center is Drude peak. And yeah, you end up. So here I think, yeah, this calculation done by Haruki. So I don't fully grasp the details, but this peak apparently has a finite width, but this is because he put some artificial widths in the calculation to make the calculation sensible. So this is basically delta function peak. And we can identify the Drude weight by the magnitude of this peak. And yeah, also here. So this is the double delta function peak in the second order nonlinear conductance. And by this amplitude, we can identify the nonlinear Drude weight. And okay, so this is small, but so he calculated the Drude weight for linear response and the F-sum frequency integral for linear response, and we can compare with this formula, Kohn formula, and F-sum formula. Well, this part is not so new, but they agree up to 3 digits or something. And now we can also compare second order response, the numerically obtained value versus the nonlinear generalization of the Kohn formula, and numerical frequency integral versus the nonlinear generalization of the F-sum rule. So now the agreement is not as good as the linear one, naturally, but still we have agreement up to 2 digits or something. So we hope that this F-sum rule and maybe this nonlinear Kohn formula could be useful, for example, to check numerical calculation. So this is tight binding model, so perhaps there is not much room for mistakes or subtle errors, but if you are going to study more non-trivial interacting models, then having this kind of general constraint can be useful, at least as a cross-check. Yeah, there is a question from Yasha. Can you elaborate on how you do? Okay, sorry. Yeah, you should ask Haruki. Sorry, I just copied his result. I have to confess. But well, yeah, this is we have exact Hamiltonian, so I don't think he has used something like Kirdish. Just a straightforward calculation. Okay, so to summarize, yeah, in the latter part of my talk, we obtained two very general formulas for nonlinear conductivity. And one of them is F-sum rule, generalization to nonlinear ones, which naturally contains a linear F-sum rule, which has been known for a long time. But it has very natural generalization in this compact expression. And the other main result is the generalization of Kohn formula for nonlinear generalization of Drude weight, which corresponds to a coefficient of 1 over omega pole in frequency space. And this nonlinear Drude weight has very similar expression as F-sum. Maybe I need 1 over V here. Anyway, very similar, but their meaning is different because in the Kohn formula, you need to find the energy eigenvalue as a function of flux or vector potential, then take derivative, higher order derivative. But in F-sum rule, you have Hamiltonian as an operator, which depends on the flux or vector potential. Then you take derivative with respect to the vector potential for this Hamiltonian as operator. Then after that, you take the expectation value with respect to the original ground state. So these two formula look very similar, but rather different. And this difference actually comes from the, physical, very different physical processes we are considering. So F-sum rule corresponds to the instantaneous response. So I just do the sudden insertion of the flux. So as a consequence of this sudden approximation, which becomes exact, I have this formula. First take derivative of Hamiltonian, then take expectation value. But the Kohn formula corresponds to the very long-term time response. So you do the adiabatic insertion. So then basically by inserting the flux, you follow the eigenstate. So you track the change of the eigenvalue of the Hamiltonian. So corresponding to that adiabatic insertion, you must take the derivative of the energy eigenvalue as a function of the vector potential as a flux. So, okay, so this flux insertion business looks very simple and to some extent trivial, but yeah, there are still some new applications coming out. So thanks for your attention.
Let's unmute and thank Masaki for his talk.
Thank you.
Okay, we have a number of questions here. Dominic Elsa, first question.
Hello. Yeah, I wanted to come back to this question of sort of the gap closing during the flux insertion. I was still kind of unclear on how this could happen because like the gap is really usually a local property of the
right,
system.
yeah.
But
so
the flux is a very global property, so it doesn't seem like the gap should see the flux at all.
Right, yeah. So I think, yeah, under some assumptions, we should be able to prove. Okay, so in some sense, Hastings has a proof for Lipschutz matrix itself without using this assumption. So in my understanding, his Hastings proof for Lipschutz matrix theorem does not directly prove this protection of the gap, but sort of supporting evidence, I would say. And also, Haruki Watanabe has a recent paper in which he shows that much of the macroscopic properties of the system is insensitive to the flux insertion of the change of the boundary condition. But he hasn't completely proved that the gap is protected, but he did show that the gap to the excited states, which you can access by local operators, applying local operators, should be protected or something like that. So well, if that is the case, then maybe the only remaining possibility is that topological, let's say, well, yeah, some kind of topological excitation. But again, topological excitation should be insensitive to local perturbation. So, okay, so I tend to agree with you. But on the other hand, I mentioned the example of superconductor coupled to the gauge field, which corresponds to long-range interaction. So I guess our intuition somehow depends on the locality of the interaction. So once you include long-range interaction, somewhere this gap protection hypothesis would collapse, I guess. But how long-range interaction exactly we need, I have no idea. But yeah, for short-range interaction, I agree. Yeah, at least my intuition agrees with you.
Thank you.
I have a question from Yang Ji Chu.
Hi, Masaki. Thank you for your talk. My question is about the translational symmetry. It seems that you need a translational invariant to have this result. And interest is about thinking about like Anderson localization or other disorders. I'm wondering, the motivation is that sometimes they have vanished linear response conductivity, but they might have nonlinear conductivity. I'm just curious if your new established method can help us understand those, for instance, a nonlinear Drude way.
Yeah, so, okay, so, yeah, maybe my presentation was not good, but so this part depends on the translation symmetry. But latter half of my talk, yeah, these are main. So this part does not, as far as I can see, does not depend on translation invariance or anything. So we can apply this to localized system. Yeah, yeah, that could be interesting. Yeah, actually, Haruki has done a little bit of computation on simple model of disorder system, but yeah, we still don't have much understanding about the subject. But yeah, this should be applicable to this part should be applicable to disorder system without any translation symmetry. So that would be interesting application. Yeah.
Thank you.
Okay, we have a question from Sreji Chuliparabil. Sreji, ask the question.
Can you go to the slide of gap protected where you made an argument about 2 dimensions?
This one?
This one. Yeah. So even in higher dimensions, when you suppose there is gap closing, if there will be a positive energy gain, right? So delta epsilon is still positive. So this means that D has to be positive, right?
Well, but it might scale like 1 over L or something.
Yeah, but
yeah. So yeah. So if we yeah. So if we how to say enlarge the definition of the insulator or make it strict which way? Anyway, yeah. So even in 3 dimension, yeah, this might be useful to derive some result. Yeah, actually, I remember Ashwin and Arun had a paper basically applying this flux insertion type argument to bosonic system. And I think they argue that even in 3 dimension, essentially my statement should hold or something. But I didn't quite understand the argument. But yeah.
In 2 dimensions,
yeah.
If you start with a system which has some electrons over the gap as well, and then when you do the adiabatic flux insertion, and if there is gap closing, and if those same states which has electrons in the above the gap come down, and the states below go up, which were also occupied, then we would have an energy gain of 0, right? But that doesn't show that it's an insulator or a conductor, right?
So you start from not the ground state, but some.
I'm looking at a system which is filled so that it has electrons even above the gap.
But you mean by above the gap the single particle spectrum, single electron spectrum has a gap, and you put some electrons above this gap.
Yes.
That's what you mean. Yeah. So here, this gap is a many-body gap. So maybe we should distinguish many-body gap from the single particle gap. But well, so yeah, I don't know if I have a good answer to your question, but so in this talk, I focused on the ground state because it's easier to discuss. But this kind of argument is also applicable to finite temperature states and so on. So if you have a finite temperature, then you have Gibbs distribution, you know, so many eigenstates contribute with some probability, and for each eigenstate we can track the energy eigenvalue as a function of flux, then take derivative, and then we consider statistical average with the same weight, because adiabatic evolution of Gibbs state shouldn't change the probability of each state. So if you define the yeah.
I was actually thinking, like, in the ground state, can't the system have electrons both below the gap as well as some above the gap? Like,
that's a single particle gap. Yeah.
We have quite a few other questions. Maybe we can take another. Hang on, please.
Okay, maybe we can discuss later. Yeah, sorry.
Okay. Yeah, sure.
Chun-Li has asked a question. Hang on. Hang on a minute.
So
I got, yeah, so Chang-Li Huang asks.
In chat window, okay.
Yeah.
Very simple question. In your summary slides, can you comment on the Hellman-Feynman theorem? Okay. Okay, yeah, good question. I guess it's related. Let's see. Okay, so I think in one definition. Okay, so one thing I can say is that the yeah, this Kohn. So one thing I can say is that I didn't fully explain the derivation, but I related the energy increase to the derivative integration over derivative of Hamiltonian. but this relation is not totally trivial, and because in general, the wave function is also developing, evolving over time, and the Hamiltonian is also evolving over time. But actually, energy increase can be related to the expectation value of Hamiltonian dH dt by the wave function with respect to the wave function at that time. So to be precise, I should write the expectation value with respect to psi of t, to be precise. But this equality is something like a Hellman-Feynman theorem. It's not completely trivial, but if you write down the equation, you can check this equality holds. So in that sense, yeah, it's kind of related to Hellman-Feynman theorem, although the final result may not be exactly Hellman-Feynman theorem or its consequence, but I guess it's at least sort of related result.
Okay, he's had his hand up for a while. Yosha Kumajani, question next.
Hi. So I also have a question about this linear part of your study. So independent of whether there is a gap in the system or not, I guess we can do the adiabatic flux insertion and we will end up with the same spectrum I had before. But if we do it too fast, we are disturbing the equilibrium, right? So, so I guess there must be some sweet spot for, or some window of parameter where capital T can be, right? It cannot be too long because you don't want the current to be dissipated. It cannot be too short because then you will be violate the equilibration. So I'm just wondering, can you put some bound on this?
Yeah, so maybe your question is about the situation where delta is actually finite in
right. So one limit from there, exactly. T has to be larger than 1 over delta. But
yeah.
What about vibration? Can we talk about that part? Because it cannot be. Yeah. So yeah.
So okay. So those factors. Okay. So this analysis, we are thinking about very idealized model like a Hubbard model or something, which has Drude weight with really delta equals to infinitesimal. But as you say, in realistic systems, there must be some finite delta and also finite relaxation to the new equilibrium.
Yes.
So yes, so I guess the
sorry, another thing is that we don't have a gap to protect us. So with a capital, I mean, no matter how large is capital T, there will be some deviation from equilibrium, and then the linear response formula cannot be really applied.
You mean the finite flux changes the equilibrium? Is that what you mean? Well, maybe I'm wrong, but my understanding is that this entire formulation. Okay, so we just start from some equilibrium state or ground state for given Hamiltonian, then apply electric field and see how much current is flowing as a response to this electric field. So this formulation does not take the relaxation into account, at least explicitly. Any problem with this? So of course, if in realistic system, real material, there should be some, extra coupling to external environment in addition to this kind of spectrum. Then, yeah, there are relaxations. So, well, yeah, so I guess in in that case, these formulas are only valid up to time less than the relaxation time scale. Yeah, I sort of agree with you said. Yeah, but here we are considering very idealized model with zero coupling to the environment. Then we can take T to infinity, but of course that's not realistic for actual material. So there will be some trade-off. We haven't really figured out that, but I agree with your observations.
We're kind of into the break period, but if we've got time for two brief questions, one from Tamagna Hazra and one from Pavel Volkov. So Tamagna, you go first.
Hi. So I have a question about this slide.
Okay.
So I guess, so when you say epsilon naught, that's the many-body ground state energy. So the Hamiltonian is defined by the many-body ground state energies and the wave functions. So it seems like the long time response is independent of whatever the wave functions are doing. Is there some intuitive way to understand why the wave functions of the Hamiltonian drop out of the second part?
Yeah, okay. Good question. I don't know. So yeah, it's highly non-trivial, but basically, I guess this is because we have this formula, this Hamiltonian, the current. So here we are only considering the uniform current. So if you consider response at finite wave vector, then I think the situation is completely different. Probably you also need wave function. But here I am only considering the response of the uniform current Q equals 0 to uniform electric field Q equals 0. So in that case, the current can be related to the time derivative of the Hamiltonian with respect to the insertion of the flux, as I showed part of that derivation. So essentially that special relation is behind this result. Yeah, I agree. So in generic physical quantity, we should need information about wave function, but here only eigenvalue is needed because of the relation between the uniform current and the time derivative of the Hamiltonian.
I see. And you made no assumptions about whether the system is topological or non-topological.
So no. Yeah, we didn't assume anything here. Yeah, just basically the assumption is just that you can, you can write down the current as a response to the electric field up to infinite order. But that should be at least physically reasonable. Although mathematically maybe highly non-trivial, physically that's what we expect.
All right, and one last question from Pavel Volkov.
Hello, my question is about the first part of the talk where you had the adiabatic flux insertion for a system with some partial occupation. So if you have a mod insulator, in principle, you're at half filling, right? So this argument would tell you that the ground state momentum is changed, and hence it's either gapless, which it is not, or it has a ground state degeneracy. But in principle, it also needn't be the case. So can you explain how this works in the mod insulator case?
You mean the spinful electron with half field means that so each side can accommodate up and down spin electron, but one electron per side. Yeah, in that case, well, mod insulator does have degeneracy because if you have nail states, then you have up down or down up, and if you form CDW.
Well, if you form CDW, you change the periodicity, so it could be that this shift of the momentum is actually trivial. But if you don't break...
So my statement is that if Hamiltonian has the symmetry, okay, so so this CDW or nail is part of this Q4 degenerate ground state. So, so this statement applies when you have periodicity translation invariance of Hamiltonian. So the Nail state or CW state enlarged as units there, but it's due to spontaneous symmetry breaking. Then spontaneous symmetry breaking must accompany the ground state degeneracy. So this theorem says that if you have half-field system, then you have to, if you want to open the gap, you must produce the ground state degeneracy in one way or another. And Nail or CDW, possibilities which is spontaneous symmetry breaking, which accompanies ground state degeneracy. So that's consistent with this theorem. So what this theorem forbids is that you cannot just open the gap without any spontaneous symmetry breaking or topological. That's it.
Well, if you consider a state which doesn't break a symmetry like an RVB state, still it will have some ground state degeneracy.
Well, yeah, that's an interesting part. So the RVB type spin decay seems to contradict with this statement, but actually this theorem only applies to torus or periodic boundary condition. Then RVB type spin decay should have a so-called topological degeneracy, which is also consistent with this. So this theorem says that you must have either spontaneous symmetry breaking, that is conventional kind of order like a Nail or CW, or you must have a topological order in order to open the gap.
Thank you.
Yeah.
That is a wonderful point to end on. These are very powerful theorems, and thank you so much for telling us all about them, Masaki. It was a wonderful talk. Let's thank Masaki for this great presentation.
Thanks, Masaki.
Thank you.
Thank you.
You stayed up late at night on all these occasions, remarkable, and remained sharp. That's great. So now we're into the break period. It's 38 minutes past the hour. We'll go into breakout rooms for 15 minutes or so, and the next talk will resume at 4 o'clock London local time. Thank you very much, and see you in the breakout rooms.